Okay, hello everyone. My name is Carlo Giacometti. I work at Wolfram Research, and today I'll be talking about what is new in Wolfram Video. I will transition immediately to the webpage that kind of showcases all of the features that we'll be talking about today. I think you should be able to find in chat a link to the same page. That's the video corridor page that kind of shows the main features of video in the Wolfram language. I'll quickly go through this and then I'll start with the presentation. As maybe many of you know, video is now a first-class citizen. It just works. It is completely integrated into the language. And we provide lots of native functionality for capturing video, for creating videos from images, from expressions, from graphics, and all variations of that. We do provide video editing functionality. We do provide enhancement and color correction in videos. This is very much related to all of the image processing functionality. We do have specific face analysis functions and video analytic functions as well, where you can operate efficiently on whole videos, having memory of what happened before, etc., etc. Leveraging all of the machine learning functionality, we do have functions that do object detection and tracking, and this is obviously very much related to the computer vision area of capabilities. And linking to the audio processing, it is very easy to apply any kind of audio processing or analysis to audio tracks that live within video files. And we do have a very extensive support for both formats and codecs for videos. So I do encourage you to go visit the video corridor page, click on the links, explore. It is a pretty fun one. With that said, I will start my presentation. So as I said, I will give a quick overview of what we have in the Wolfram language that is related to video objects, video processing, video analysis, video computation in general, I would say. So first of all, in case you have never seen it, this is what a video object looks like. So here I am creating a video from a file that's somewhere on the internet. It gives you a nice playable GUI. And maybe if we want the audience to also listen, maybe I will set the correct audio device. And let me share the sound as well. Sorry about that. But hopefully now the sound is coming through as well. So nice little player, nothing fancy, just convenient. The video file could be stored in a cloud object. And similarly, you got exactly the same thing. And it could be a local file as well. And you can definitely compute information and properties of it. You can see here, I get durations, raster sizes, and information about the video tracks, including the encoder, well, the encoding, and the frame rate, information about the audio tracks, etc., etc. Functions like duration work directly on the video. Functions like image dimension works directly on the video, or audio channels as well. So this kind of is hinting at a theme that we'll look at today. Functionality that was originally developed for other data, for example, image or audio in this case, has then been overloaded to work natively on videos, to seem familiar and to provide an easy entry point to the user that is already familiar with other areas of the Wolfram language. By the way, if you have any questions, feel free to post them in chat, and I'll try to reply them as well as I can. So I will start talking about how to generate videos. We've seen how to create videos from files, from remote files, cloud objects, etc., etc. But what if I want to generate a video from scratch or by processing a different video? Snippets video is a function that takes an input video and then a list of times or a list of intervals, and this will trim that video around. And it is kind of a convenient way of extracting salient clips from a longer video. Grid video instead, the idea is that you can create a synchronized collage of videos. In this case, I have this set of videos in a folder. There's the cat that you can never go wrong with, other cats, some dogs. And with grid video, they are all placed on the same canvas and synchronized. And you can see how I can restart. And that works very easily. And there are options to control how this looks, like background and spacings, etc., etc. And if you want to control the positions of videos, you can also use a matrix, and you can use missing to indicate where you'll have blank spaces. In this case, I injected 2 blank spaces in the second row, first column, and first row, second column. The synchronization is exactly the same. And lastly, another way of creating videos from videos is overlay video, where you can take an existing one and place some overlay on top of it. In this case, we just have this image of a spiky. In another case, you can also overlay a video onto another video. And in this case, they are synchronized and overlaid. The overlay can also be a function of time. In this case, I'm overlaying to the video with the curse. I'm overlaying this spiky, which is rotating as a function of time. So this gives me this nice rotating and bouncy spike in that lower right corner. And you can control the placement as well of the overlay. So these are some easy way to create videos. As an aside, I want to point out a few common video generation options that you can specify in all the functions that I'm talking about today that generate videos. You can control the encoding, and you can see here we have a pretty extensive list. Different encoders will have different performances. Some will be faster to write, some will be faster to read, some will be more compressed, some will be less compressed, etc., etc. Some will support alpha channels. But yeah, the choice is left to the user. There are some defaults, obviously, but there is a huge variety that can be used depending on the application. Another important common option is generated asset location that controls, since with videos, we're always talking about files, either on the internet, on the Wolfram cloud, or on your local machines. It's always a file somewhere, right? So the generated asset location will let you control where that file will live. And you can specify it, for example, like this. I am generating a new file in my home directory. You can also specify a directory. So then this file will be automatically named in the directory that's specified. And there is a dollar variable. Generically, the value, let's look at this, for example. Look at options. of video generator, we can see that generated asset location is set as a rule glide to the value $generated location. So you can, for example, if you did this, all of the video generating functions will end up producing file within this directory. This is kind of a convenient global way of changing the behavior of anything that generates videos. Another option that is important is raster size. Very intuitive. How big is the frame that you're generating? And many of the functions that I'll be looking at today, both generating and processing, support parallelize. In this case, I can just generate something that is kind of slow. The rasterization operation takes some time. And using parallelize, the frame generation part of the operation is effectively parallelized over all of the available kernels. And this, depending on what you're doing, can give you significant speedups. So these are kind of things that are good to keep in mind when generating videos. Back to video generation in general. Slideshow video is something that makes it easy to generate a video from a list of images. It just has some image for some amount of time. And it is easy to control how long an image is shown by specifying the time for each image individually. So this will last 1 second, this will last 2, and this will last 5. And similarly, a time series can be used. The advantage of a time series is that it has some interpolation between the points.
Recording in progress.
And you can see how it does essentially a fading transition. This is exploited in the video generation as well. Another important video generation function that I feel like is probably the easiest to use for someone that is already familiar with the Wolfram language and has experience with using important constructs like manipulator table. Let me show you the comparison. So here I am creating a manipulate with a variable t that runs from 0 to 1 that produces a constant image with a hue that depends on that variable t. If I scroll that variable t, I get this change in hue of the image. Animation video works exactly the same. I have a generic expression, and I have a variable specification. Unlike manipulate, animation video only supports one variable at a time, but obviously, if one has multiple variables, they can always be parameterized as a function of a single one. So yeah, this video should be exactly the same as that manipulator we have seen. So the hope is that this construct will be very familiar to people that are already users of the Wolfram language. And in general, I feel like it is a reasonably simple concept to understand. The syntax, again, same as manipulate and table. Here, I am defining a rot variable that goes from 0 to 2 pi, and I am just rotating the image of the cute dog image rotate. So generating the frames. And we have the rotating cute dog. Again, super easy to use in terms of syntax. And I've shown you functions that produce images like image rotate and constant image, but animation video also works with stuff that evaluates to some graphic, and that will just be rasterized. So here I am solving some differential equation, and I am animating the 3D solution, the 3D visualization of the solution to that differential equation. Yeah, I've just created a video of a complicated mathematical structure with almost zero effort. As you can see, this is just a contour plot of the solutions animated through a variable a that runs from -2 to 2. Another video generating functions, and yeah, we do have a lot of video generating functions because we do feel like that is an important part of video for the Wolfram language, right? You might be a user of the Wolfram language in some completely unrelated topic, but you might want the output of whatever you're producing to be transferred into a video to share on social media, or it might just be the easiest way to communicate what you're trying to communicate. So we are trying to provide as many ways to produce videos easily as possible. Frame list video and frame table video are, I think, the simplest of these. They just take a list of frames and they chuck them into a video. So this generates the video, this extracts all the frames, and as you can see, the frames of the video have just these images. Frame table video is exactly the same thing. The only difference is that it doesn't really require to have all the images in memory already. It is hidden into the video context. It hasn't made it into a system function yet, but it is easy to find and hopefully easy to use. It works exactly like table. You can see here how I define a file variable and then have it iterate over a list of files, and that just generates exactly the same thing. So it's just a cheeky alternative that might be convenient in terms of memory usage. Another high-level video generation function is called tour video. And the idea is pretty straightforward. You have some two-dimensional construct, which might be an image, might be a graphics object, and you want to kind of pan and zoom and explore that two-dimensional construct. So, for example, you start with a giant image like this one. I will delete it so my notebook is then not popped down. As you can see, pretty giant. And then you can specify the steps of the tour that you're taking around this two-dimensional construct. You can see I have step 1, which tells me I want it centered around this position with this width. And step 2 tells me that I want to be centered at this position with a much smaller width. So we'll move and kind of zoom in at the same time. And I see that there is one question about what happens of images of varying aspect ratios. That is a very good question. I can show immediately, I think, within here. So if let's say I just crop this image to a completely different aspect ratio. Let's see, can I do this? Let's do I want to. Oh, that did something strange, but it definitely got some cropping. You can see how the image is stretched in the video generation. Now, if you want to specify how this is handled, you can specify the confirmation method option. Let me see if there's some usage. Yeah. And you can specify it to do things like stretching, filling, or cropping. So there is some default behavior. Those are handled automatically, but you can control how that automatic confirmation happens using this confirmation method option. Going back to video, another way of we've seen here, we've specified 2 positions and widths that happen at 2 different times. You can also specify the position, for example, as a function, or in general, everything as a function of time. Here I am specifying a function that takes the time and produces a position and width. This will be the position as a function of time. And you can do exactly the same thing. And this will spiral around the image and zoom in as well. You can programmatically do all this as well, right? You can take famous physicist summit in the 20s, I think, image, maybe earlier than in the 1920s. Don't remember when this was. Anyways, you can use find faces to programmatically figure out where all of these faces are, and then find the shortest tour between all of these things. We can see all the faces right here. And you can just give tour video the image and the position of all of these. And this will just generate a video zooming over each face. So this way we programmatically generate some tour rather than manually specifying like we've done in the previous examples. There is video generation from webcams. So, yep, we have our trusty video capture that works as you'd expect. It has a nifty preview that hopefully works okay. And you can just record. And this will produce a nice video. And similarly, you can do exactly the same from screens. Record what is happening on my screen. And this will produce another video. So these are util. I'm sure everyone has fancier video recording software, but this gets the job done, and it works right from the notebook and produces not a file, but an actual video object. So that is can be kind of convenient. Now moving to video editing, and here I'm just giving a quick overview of the basic things that can be done. You can do temporal editing with video trim, video split, video join, video delete, video replace. So here we have our video with Bullfinch. That is about 15 seconds long, and you can trim it and extract the part between seconds 1 and 2. You can similarly video split it. If you want, there's video join as well. And all of these do pretty much what you'd expect from their names. One thing that is kind of less intuitive than splitting and joining and deleting and replacing is combining. When you're combining different videos, the tracks are just stacked on top of each other. So for example, if I combine video 1 and video 2, the resulting video will have the video tracks from both of these that play at the same time, and you will be able to select which track is playing in the menu from the GUI. In this case, we only have multiple audio tracks and multiple subtitle tracks. Video combine can also be a useful tool for combining a video that doesn't have any audio, and you can just combine any kind of audio signal with the video. Image editing functions, as I've mentioned before, a lot of them have been overloaded to just accept videos as inputs. So if we have one question, does screen capture return a video without or without sounds? You can see here, if I look at, screen capture, let's look at information of out 190. Yeah, well, let's do it like this. You can see here it returns by default just the video screen capture. However, it does have an audio input device option that by default is set to none. If I look at the options, well, I guess it is set to automatic, but by default there is no sound capture. But as long as you specify something that is not none, it will capture synchronizing a synchronized audio as well. Yeah, so I was saying image functions now just take video, for example. So here I am cropping the video of the bird and to just this dimension. Similarly, image rotate, that's the same. Color negate is another example of image processing function that has been overloaded. Image effect as well has been overloaded. So there is a lot of room for creative effects as well. Another thing that we introduced in, I think 13.2, so fairly recent, is all of these functions, right? You have image effect, for example, and stripling, or image rotate 20 degrees. And this will rotate all of the frames by the same amount. What if you wanted to have a rotation that evolved as the video evolves? So in this case, you can specify a function where the function is a function of time. So this will rotate each frame by this amount, where slot will be the time at that frame. So at time 2, it will just be rotated by 4 pi divided the duration. And you can get stuff like this. Obviously, this is just a silly example, but it shows the how powerful this kind of syntax is. Or image effect, for example, you can see how this is a pure function as well. It takes the time as an argument. And let me reset playback. And you can see how the nested composition parameter evolves over time, or image transformation as well, where you have the function, the transformation function that is a time evolving function as well. And it is very easy to apply any kind of audio processing to videos. So if I have something like this is just a video object. If I just specify audio that, I get an audio object that is just the audio track of that video object. And with audio track apply, I can apply any kind of function to the audio track. And then this produces a video with the transformed audio. In fact, if I look at the spectrogram of that, you can see how this was high-pass filtered. So a lot of different processing functionality that draws from both the image processing code base and the audio processing code base, and kind of provides a way that should be already familiar to act on video objects. We have some generic functions that do video processing as well and video analysis. These are kind of very powerful constructs. Oh, before I get to that, another question: is there a limit to the max frame rate of the footage? Well, it all depends which codec is being used. I think there are limitations that are codec dependent. You'll have to, whichever codec you're using, you'll have to get yourself informed on what that would be. However, all of those should be hard-coded. So you could specify whatever, and that will be modified. So if, for example, if you say video generator of something and a frame rate that is higher than the codec supports, we internally should be able to renormalize that to the maximum value supported by the codec. But yeah, I'd assume there is a limit to the max frame rate. It's a codec dependent thing, and I don't know what the exact thing is. So generic functions, video frame map. This is pretty straightforward in what it does. Let me give the easiest example of this. So for example, I want to map color negate on the video of the weird fish. And this does just that. This takes this function and applies it to each frame of the video and produces an output video. You could also do something like this. The second argument tells you how this is done, right? But in the default, you take frame by frame. If I specify the second argument, this is the second and third argument are kind of work like kind of partition does. So this takes partitions of 10 frames and skips 10 frames. So in this case, blend is applied to a list of 10 images. And as you can see, those frames are blended. So there is kind of motion blur. Super straightforward, but the complexity of this will be defined by the function that the user will use here in the first argument. Video map is kind of the same idea, but instead of just passing a frame or an image to the function that is specified to the user, video map passes a whole set of data. We can see what that is. We can see what it is doing something silly like this. So this will do the first iteration. You can see how video map provides me with the frame index, the input frame index, the current time, the time interval that corresponds to the frame, the actual frame, and the audio snippet that is synchronized with that frame. So in this case, I can apply a function that depends both on the image and the audio track. And here I have an association of two functions. One that is the function that produces the signal, and the other, the frame, and the other is the function that produces the audio. This just transfer the audio track to the result in this case. And you can see how the hue changes in a synchronized way with the audio track. Again, simple function, the complexity all lies in whatever the user will specify in this first argument. And this is a whole family of things, right? Video frame map, video map time series. Video map produces video. Video map time series takes the same kind of function with the same kind of arguments, but places the output of the user function into a time series. So for example, here I'm looking at the intensity centroid of the video, or something related to the intensity centroid. and I'm putting the result of that in a time series. Oops, clicked the wrong thing. And as you can see, I just get a time series of that. And I can use that time series to control, for example, the creation of something using overlay video. I'm taking the input video, and then I'm producing a point whose position is determined by that time series. So you can see here the point will be located where the centroid of the frame is. And similarly, video map list. Sometimes video map time series is bound to fail just because the output result is a time series, and that has restrictions on what the dimensions of things are. In this case, dominant colors produces a list of different dimensions at each frame. So this fails miserably. Video map list does exactly the same thing, but instead of populating a time series with the results, it populates a list. So here you just look at the dominant colors of each frame. So for example, these are the dominant colors of frame 1, frame 2, frame 3, etc., etc. So these are two video processing function, video frame map and video map, and two video analysis function, video map time series and video map list. And they all kind of work in the same thing, in the same way, just the output is different. And I would say very much depends on the application, which one you would choose. Some slightly more funny examples. This is just a video of some waves on the beach, and I can solve the equation, the differential equation for a bouncing ball as a function of time. And then I can just overlay video of the beach video, and then this is just an image of a beach ball, and this rotates as a function of time and moves as a function of time as well. So you can get funny things as well. So you can combine like solution of differential equations and video generations very easily. Obviously, this is a silly example, but who doesn't like silly examples? In this case, I am downloading a video of a dog running across the frame. And what I am doing here is defining a function that takes a frame and calculates the position of a dog within that frame. This is one of the machine learning based functions that we have within the whole image processing suite. And the way to apply that to all frames, as we've seen before, is just to do video map time series of the function that finds the dog all across V, which is the video. And as you can notice here, I'm using parallelize to speed up that detection. And here I'm just overlaying the original video with the parametric plot of the position as a function of time. Let's go to the beginning. So now the video appears, and now image position starts tracking it. And so you have an easy combination of image processing, computer vision, machine learning, and video analysis and video generation in a single simple example. This was based on a example, and that was made for the release of version 12, so a little while ago. But now the video generation part is much more streamlined. It takes a picture of a car and a mask, and it has some functionality to look at compute contours derived from the image. those are applied to the image using fold list, and then they are overlaid onto the image itself. So you can get this funny drawing effect as well. Another topic that I want to, I've already mentioned a little bit, but machine learning for video. We do have a set of video networks in the Wolfram neural net repository. Not many at the moment. There are many more in the pipeline that will be released soon. However, it is very easy to process videos using the frame map or similar using image networks. And here the list is pretty extensive. I have here, oh no. Well, something happened. Let me reopen that notebook. Well, that was mildly unfortunate. Okay, let's see if we can restore our presentation. Okay, so we have a YOLO variation that we retrieve very easily from the neural net repository. This might take a second to wake up. And we've defined some utility functions here to post-process the output of the network as well. So these should be standard operations for anyone that has dealt with neural networks before. We have a simple video. Hopefully we'll appear in a second. Here we go. Just a cute dog running around. Well, there's something so here. I can display a pre-computed output. You can see what happens if you apply the network on a frame of the video. It produces bounding boxes that are classified, so it knows that this is dog, and it gives me a bounding box, and all of these are people, and it gives me bounding boxes for those. So I can easily define this function here. So I am highlighting the frame and with the result of the network on the same frame. And as a result, a video where this is classified frame by frame, following the dog, following all the objects that are appearing in focus. So again, this is an easy way to exploit all of the very powerful computer vision functionality, neural network functionality directly onto videos. I want also to showcase a few things from users. I recommend looking at Wolfram community, at the video processing group, for example. There is a lot of activity there. There's one example, taking an input video and making a cartoon version of it. There is also a lot of, there is also some contribution in the Wolfram function repository from users. For example, video color map produces an image with the colors of each frame within the video. There's video reverse that takes a video and reverses the whole thing. And I'm expecting more contribution to the Wolfram function repository, both from external users and from us as well. If there is something that we find is useful but doesn't really deserve to get promoted to the system context, we will probably just put it in the function repository. So these are the main things I wanted to make sure to touch on today, all of the more basic usages and all the important usages, I would say, of video in the Wolfram language. I wanted to quickly mention a couple of more advanced topics. So how all of this works is, oh, sorry, there is one question is there some kind of watermark that can be applied to videos? Well, that is what I showed earlier, right? If there is no function that does that does explicitly watermark, but for example, with overlay video, you can create whatever watermark, place it wherever you want. And in this case, you just have it overlaid over the original video. This can be any kind of image, transparent, non-transparent, doesn't matter. So this is how I would deal with producing a watermark overlaid to frames. Yeah, so how do we do all this? The main ingredient that we have to produce videos, read videos, etc., is the FFmpeg library. This is used as a backend through the FFmpeg tools backlet. And if you look at it, it is right there within the layout. So one thing to note, we do ship a version of FFmpeg within Mathematica, but because of licensing restrictions on several codecs, it means that we don't natively ship all codecs. But what users can do, and what we point out users to do, is to install independently a full version of FFmpeg on their system. And the first time you use the video functionality, if you don't have it installed already, Mathematica will pop up a dialog that will give you some instructions on how to do that on the different platforms. It is very straightforward. On Mac, for example, you can use MacPerts or Brew. On Linux, usually is supported by the distribution that you're using. On Windows, we can handle all of the download and install from within the Mathematica session. So it should be easy for users to get the most out of it by installing the full version of FFmpeg on their system. And the fact that we use this FFmpeg tools backlet comes with some advantage. All of this low-level functionality is not particularly user-friendly, but it is available to all users. If you look here, I'm looking at the FFmpeg tools back video context. And it is documented, at least a bare bones version of documentation. So if anyone wants to go really as close to the C++ level as possible, this is the way to do it. And this is how we've built all of the video functionality in Mathematica, in the Wolfram language, by interfacing the C++ code in the FFmpeg tools backlet with Wolfram language. So if anyone wants to be as efficient as possible or do complicated operations, this is a good place to start. There is no guarantee that the API for this backlet will not change version to version, but it is a good exploration playground. Another thing, kind of advanced topic, is FFmpeg natively comes with a lot of different filters. So, for example, let me see, video filters. This is something that applies a blur filter, and there is a giant list of all of these. And we do have a shortcut to apply any kind of filter in this case. We define our video. Spelling is a useful skill. In this case, I am just using the reverse filter. So this is just that video backward. Or here, I'm using the pixelize filter and specifying some parameters. And you could even, I think, you should be able to apply a list of two filters. First, pixelizing and then reverting. So the syntax for this is not too complicated. So this is filter name. And then a rule of parameter goes to value. And in this case, I am applying two filters, one after the other, and the second filter doesn't have any parameter. So again, these are very advanced usages that are not documented. They might change over time. It is just something that if you know the operation that you want to do, and you know that there is an FFmpeg filter that is very efficient, this could give you significant time and memory savings. This is just something that is interesting to know about. And with that, I will point you again to the video Correa page. Do explore there. And I think that is pretty much all of the things I wanted to make sure to present today. And let me know if you have any questions.